In this lesson, we discussed how to build formulas relating physical expressions. After taking a look to the usual formulas we have used in physics and engineering, we analyze if these formulas are arbitrary or contrary, they must satisfy some requirements. We distinguish between fundamental and secondary variables, and also between ratio and interval scale variables. The final conclusion is that we must be careful when building models because we can have serious problems if we do not respect the required and necessary rules. At the top of the slide, we have some well-known formulas used in physics that relate physical variables. A careful analysis of these formulas leads us to the conclusion that they are monomials of the involved variables or ratios of monomials, a very special type of functions. Then the following questions arise. Is there any reason for this to be that way? Is any formula for a secondary variable valid? If it is not, what are the conditions to be satisfied by a variable to be valid? These and other questions will be answered in this lesson. I invite the reader to walk with me in this analysis to understand that the problem is worth of a detailed study and see the crucial role played by functional equations. To start, we must distinguish between ratio and interval scale variables. We define these variables based on the way we change units of measure. Ratio scale variables change scale units by the formula y equal to kx. Some examples of scale variables are length, time, and mass. For example, the change from feet to meters, kilometers, or inches can be done using factors k equal to 0.3048, 0.003048, or 12, respectively. Interval scale variables change origin and scale units by the formula y equal to k times x plus a constant a. Some examples of interval scale variables are time, temperature, and location. The change from Celsius C or Reaumur RE to Kelvin K degrees can be done using the expressions K equal to C plus 273.15 and K equal to 1.25 RE plus 273.15 respectively. I invite the reader to think about the possibility of avoiding interval scale variables. In other words, to answer the question, are interval scale variables needed? Is the use of the Kelvin unit system a solution for eliminating them? If this is the case, the problem of law of science simplifies a lot and many problems would be avoided. In a physical system, there are some fundamental variables such as length, time, and mass from which secondary variables can be defined. The fundamental variables can be chosen in several ways, but they must be such that all secondary variables can be calculated from them. If we take logarithms in the monomial or the monomial ratios, we obtain linear combinations of the logarithms of the fundamental variables, which must be a basis for generating all possible secondary variables in the simplest way. Therefore, the concept of linear space and basis, or cone and set of generator edges, is behind these conditions for the fundamental set of variables. Secondary or derived variables are obtained by formulas that relate them to fundamental or other secondary variables. Some examples of secondary variables are speed, acceleration, energy, etc. However, not every formula generates a secondary valid variable, but only those satisfying some extra conditions. It is necessary that if the scale or origin of the variables involved in the formula change, an analogous change in the result variable occurs. That is, the structure of the formula must be maintained by changing the origins and units of measure allowed in all variables. In other words, the formula should remain invariant under location and scale changes. The very relevant and beautiful functional equation 1 at the top of the slide explains the conditions we desire for a valid formula u of x1, x2, xn to be a valid formula. We want that when transforming the fundamental variables x1, x2, xn by interval scale changes, the secondary variable experiments an interval scale change whose factor r and location parameters are functions of the parameters used for the fundamental variables. note that we use the letter R for ratio factors and the letter P for location parameters. I invite the reader to dedicate some time to understand in depth the meaning of this functional equation. Once this equation is fully understood, we can say that the reader will be able to appreciate the deep message that we must send to researchers looking for formulas relating physics variables in order to avoid serious problems. Equation 1 shows the most general situation, including different ratio scale and interval scale changes. However, some simpler particular cases can occur, depending on whether or not the location or the scale changes exist for the fundamental or the derived variables, or whether they are homogeneous or heterogeneous for all the variables. In this manner, we can deal with very many different situations. Several particular cases of equation 1 will be studied next. Next, we discuss and analyze some particular examples of equation 1, but not all. We call our first case the loss of a science 1 model, which is built for secondary interval scale variables and ratio fundamental variables with identical ratio scale. For this case, we have the following theorem. The most general function representing a real dependent interval scale variable when it is assumed that all independent variables are ratio variables of identical scale, that is, the general solution of the functional equation in 2, where R is a non-negative scalar, is the one given below, which has 3 possible expressions. It is relevant to discover that an initially n-argument function u converts to an n-1 argument or constant function f, that is, a complex problem reduces complexity thanks to the conditions imposed by the functional equation 1. We remind the reader that here x1, x2, xn are ratio scale variables and the secondary variable u is an interval scale variable. A particular case of the previous equations occurs when the secondary variable is a ratio scale variable. In this case, we have the following theorem. The most general function that can represent a ratio scale dependent variable when all independent variables are assumed to be ratio with identical scale variables, that is, the general solution of the functional equation 3 that reflects this property is 4. Note that here x1, x2, xn are ratio scale variables and the secondary variable u is an interval scale variable. A first and interesting example is the case of the area of two-parameter geometric figure. Consider a geometric figure defined in terms of two length parameters x1 and x2. Then its area A must satisfy the functional equation in 5, which according to equation 4 has general solution in 6, where C is an arbitrary constant and F is an arbitrary function. However, we know that if the lengths are multiplied by a factor r, the areas will be multiplied by r squared. So, the formula that gives the area of this family has to be of the form in 7, where f is any non-negative function. Expression 6 not only gives all valid formulas, but says that any other formula is invalid. The reader should think about this, that is common to all functional equations, because they lead to the set of all its solutions, but also indicate that any other function do not satisfy the stated conditions, a property which becomes relevant when modeling. Our next example refers to ellipses and rectangles. Therefore, the formula 7 is valid for any family. In the particular case of the families of ellipses and rectangles, we get the f functions that lead to the two formulas below, respectively, which give the areas of the ellipse as a function of its semi-axis and of the rectangle as a function of its sides. This reveals us a definition of the pi number as the quotient of the area of an ellipse and that of the rectangle defined by the semi-axis. The extension of this formula to the case of more than 3 dimensions is immediate and will be given in another theorem. As an illustration, we consider the case of the Madrid Royal Palace, whose plane can be defined based on the two parameters A and B as indicated in the figure. We want to calculate the area A depending on A and B, that is, capital A is assumed to be a function of A and B, where A and B are length parameters. According to the previous result, the function f must be as indicated, with which we need to determine the function f of one argument instead of a function of two arguments. This function is the one given in the slide. It is curious to see that the formula of the area is the same for all palaces having the same topology, and that it has the form above, where the function f is a second-degree polynomial in the dimensions ratio b over a. We remind the reader that this ratio comes from the Buckingham theorem. By giving different values to parameters a and b, different forms are obtained of the palace, as seen in the figures. However, all of them keep the same topology. Next, we deal with what we call laws of science 2, which deals with interval scale variables. In other words, the case of interval scale variables that depend only on scale variables is considered, although their ratios may be different. Here we have the following theorem. The most general function that represents allocation and scale real dependent variable when all independent variables are assumed to be scale variables, not necessarily identical, that is, the general solution of the functional equation 8 is the one given in 9 or in 10, where we have logarithms or potential. The next theorem is an important particular case of this theorem. In this slide, we deal only with ratio scale variables and have the following theorem. The most general function that a real scale secondary variable can represent when all independent variables are assumed to be scale variables, not necessarily with identical ratios, that is, the general solution of the functional equation 11 is 12, where a must be different from 0 and at least one c sub I must be non-zero. We know that all the physical formulas given at the beginning of this lesson are of the form 12. Note that now we have no logarithms anymore. Thus, it was not a coincidence because they must be that way. Next, we deal with our laws of science 3a model, and then we have the following theorem. The general form of dependent real value variables with interval scale non-constant and continuous at a point when all fundamentals or independent variables have interval scale with the same value of r, that is, the general solution of the functional equation 13 is 14. For our laws of science 3b model, a particular case of the previous one, we have the following theorem. The only non-null solution of the functional equation 15 is 16, where b is an arbitrary constant. The proof is very simple because it consists only on making p, b, and the c constants equal to 0. This example discusses the case of areas of geometric figures. Given a geometric figure such that its area depends only on a single parameter, such as a circle, a regular polygon, a regular polyhedron, etc., we call f the function given its area, where x is the associated parameter, radius, side length, etc. By dimensional analysis, it is easy to observe that this formula must satisfy the indicated functional equation, that is, the area of a figure with parameter r times x is r squared times the area of the figure with parameter x. Since it is the equation of homogeneous equations, its solution is the one indicated below. Note that c is equal to pi for a circle of radius equal to x, c equal to 1 for a square of side x, and c equal to 6 for the lateral area of a cube of edge length equal to x. This table gives the areas of regular polygons as a function of the side length x, where the constant c is a function of the number of sides. Similarly, the volume of a family of figures, sphere, regular polyhedron, etc., depending on a single parameter, is such that the functional equation at the top of the slide holds. Thus, its solution is c times x raised to the third power, where c is a constant which depends on the family being considered. As an example, for the sphere of radius x, c is 4 times pi divided by 3. The table shows the lateral areas of volumes of some well-known regular polyhedra. In this lesson, we have seen that the laws of science have an analytical form that is restricted, but very simple, so that other alternatives are not valid in the indicated sense. In particular, most formulas that we have used in our work responded to that model. However, it is possible that we have encountered other formulas which do not respond to the same model and that must be avoided. Finally, I hope you will be surprised with these results. which you had never thought of before. I invite you to follow the next lesson dedicated to functional versus differential equations, in which we show that functional equations is an alternative to differential equations. In fact, most problems that can be stated as differential equations can also be stated as functional equations.